A lot of interesting stuff happens in the hallway. It happens, you get to walk out of a session and there's a collective experience that you just went through. And so there will be a hallway conversation that springs up discussing the material.
Hi, I'm Christina Peterson. I'm from the University of Central Florida, and I'll be presenting today with Kenneth Lamar, and we will be presenting a persistent hash map for graph processing workloads and a methodology for persistent transactional data structures. So here's an overview of my talk. I will introduce persistent memory, give some use cases, and explain the pitfalls. And then Kenneth is going to talk about his persistent hash map. He'll go over the design goals, methodology, explain how he achieves persistence, and then give some performance results. And then I'm going to present persistent transactional data structures. I'll give the design goals, the methodology, and some performance results, and then we'll conclude with a live demonstration. So persistent memory is a new tier of memory. It sits right between DRAM and NAND SSD. And the benefits are that it's non-volatile storage, byte-addressable, it provides higher density than DRAM, and has access latencies closer to DRAM than storage. Persistent memory is commercially available through Intel Optane DC persistent memory, so it's in use today. So here's the traditional hierarchy. We have our storage, which is the bottom tiers of this hierarchy that are non-volatile. And then we have the top tier, which is the volatile. And this includes DRAM, the CPU caches, and CPU registers. Also, the cost goes up per gigabyte as we go up the tier, and then the latency decreases as we go down the tier. So now we have the new memory hierarchy has persistent memory right in the middle. It's non-volatile and has capacity that's close to NAND SSD, but it has latencies much closer to DRAM. And so there's design trade-offs for any tier of memory. So here's some statistics of persistent memory compared to DRAM and NAND SSD. So DRAM is volatile, whereas persistent memory and NAND SSD are both non-volatile. So DRAM caps out for capacity at about 64 gigabytes, and persistent memory is max is at about 512 gigabytes typically. NAND SSD gets to about 1 terabyte in the general case. So persistent memory latency falls between about 0.1 and 1 microseconds. So NAND SSD, if we look at the fastest time of persistent memory, it's about 1,000 times faster than NAND SSD. And if we look at the slowest latency of persistent memory, it's about 10 times slower than DRAM. So we can see that our latency is much closer to DRAM than to the NAND SSD. So endurance, DRAM is a clear winner. It's got about 64 times 10 to the 7th petabytes written. Persistent memory has about 360 petabytes written, so that's a lot less, but it's about 1,000 times better than NAND SSD. And then for the cost, I retrieved these costs around mid-October, so the prices are probably have even gone up now since at this time. But the cost for DRAM for about 64 gigabytes is $5 per gigabyte. For 128 gigabytes, which it's not common, but it's been done, that's about 7.5 gigabytes. And the price per gigabyte is going to increase with increasing densities because it's difficult to pack a lot of DRAM into a single module. So if we were to be able to create DRAM at the capacity of persistent memory, it's going to be a lot more expensive than that $16.3 per gigabyte for persistent memory. And NAND SSD is 11 cents per gigabyte. So if you have memory that you want to store, but you're not going to touch it or update it, then NAND SSD is the way to go. Otherwise, persistent memory is a much better choice. So there's many use cases of persistent memory. For metagenomics, the genome fragments can be stored in persistent memory, and a persistent hash table can be used to look up those genome fragments. For astronomy, an optical telescope may collect large data sets, and then a persistent indexing structure can be used to maintain these data sets. And then for graph analytics, the structure of the graph can be stored in persistent memory. And then graphs often have very computationally expensive operations. So we can use scalable checkpointing so that if we have a crash mid-operation, we can always revert back to that checkpoint and resume our operation without losing all that expensive computation that we've done previously. So if we look at the common characteristics of these use cases, the data sets are very large. They can include up to trillions of data points. So we need high capacity. The data sets may also encounter a large number of updates, so we need high endurance. Also, data set updates are computationally expensive. So we want non-volatility for that checkpointing. And we also want low latency so that we can perform those updates as quickly as possible. So let's take another look at our table. So for high capacity, NAND SSD is the clear winner here. But when we look at endurance, persistent memory has a much better endurance than NAND SSD. Also, we need non-volatility. So either persistent memory or NAND SSD satisfies that criteria. But persistent memory has latency that's not too far off of DRAM. It's only about 10 times slower than DRAM. So in this case, persistent memory is the happy medium. But with all these positives, there's also some pitfalls. In particular, there's architectural limitations. The caches and registers are expected to remain volatile. So this can cause the persisted data to be in an inconsistent state if the stores prior to the crash were in the cache but not yet written to persistent memory. And so the instruction set architectures provide instructions for the designers to be able to ensure durability and ordering. So for example, the x86 ISA provides a cache line writeback, and that provides durability, and then an sfence to provide ordering guarantees. But even the usage of the cache line writeback and the sfence is problematic. So here's a very simple code example where we're going to do a compare and swap. And compare and swap is an atomic instruction, accepts a memory location, an expected value, and a new value. And if the dereference value of the memory location is equivalent to an expected value, then the memory location is updated to the new value and true is returned. Otherwise, no change is made and false is returned. So let's take a look at this example. So assume that node A is initially connected to node D, and that link is persisted. And so now we have thread 1 that wants to come and insert node B. So it's going to create node B, its compare and swap succeeds, but then it's delayed. So it never gets to persist that link. So then thread 2 comes along. It's going to see that link in the cache. So it's going to go ahead and traverse to node B. It's going to insert node C and persist those links. And then it's going to successfully do the cache line writeback and sfence. Now there's a crash. So what happens is that node B and node C are no longer reachable, but they were reachable in the state prior to the crash. So this violates crash consistency. So there have been correctness properties that have been defined to be able to define correctness for persistent data structures. Crash consistency is a property where an application can be reverted to a consistent state, recovered to a consistent state after the crash that was consistent with some state that was valid before the crash occurred. Now, this is good for reads and writes, but it doesn't account for data structure semantics. So that's where durable linearizability comes into play. So durable linearizability not only requires that the data, the recovered state is consistent with some state before the crash, but also that state is consistent with correct according to data structure semantics. And so for that reason, durable linearizability is one of the go-to correctness conditions for persistent data structures. And so we're going to go into the design of a persistent hash map. And so Kenneth is going to take over.
All right, hey there, everyone. So my name is Kenneth Lamar, and I'm going to talk about a persistent hash map design that I worked on in my research. So for starters, let's talk about the settings. So what we partnered with Lawrence Livermore National Labs. They have some experts on graph analytics problems, really large ones that deal with potentially billions of vertices. And our lab mostly focuses on concurrent data structures, which are high-performance data structures that allow threads to access that same shared data structure in shared memory. And so we wanted to figure out how we could have a sort of meeting of the minds, how we could turn this into something useful with persistent memory. And so we decided to target the hash map. It's a fundamental data structure, commonly used in graph analytics problems already, but we found that there weren't a lot of high-performance, non-volatile memory options out there. So we set our design goals based around this graph analytics problem. So we wanted it to be read-optimized, where persistence doesn't need to flush or fence after the first read, was kind of what we wanted to be able to do. We also wanted to prioritize runtime over recovery. So we wanted to persist as little as possible and recover as much as possible. We also wanted a compact representation with few cache misses. And so we accomplished that using arrays and an open addressing sort of layout. And we also wanted to minimize the overheads of memory management because persistent memory allocators are relatively immature at this point. So at this point, we decided to try to focus on allocating large table chunks. So the design that I worked on and published is the persistent concurrent hash map, PMAP for short. It's non-volatile, so when it crashes, it can safely recover with these correctness conditions like Christina was discussing. It's lock-free, so we guarantee system-wide progress, and it will scale up with multiple threads. It uses an open addressing approach where we have in-place keys and values rather than a bunch of pointers. And it's set to be resizable, and it can both expand and shrink, which can be somewhat difficult in a lock-free environment, but I was able to pull it off. And the operations we support include standard ones like insert, replace, remove, and get, but we also support an update operation, which is an atomic conditional replace. In a lock-free environment, you can't get a value and assume that it hasn't changed before you can run your replace. So this value was important so that we could make sure that that value matched what we expect. It's useful for things like perhaps a counter that increments. So here's the design overview of my PMAP design. So the way that it works is we have several different levels that are part of the resizing scheme. And the sections that are in gray are the persistent sections. Everything else is stored volatilely. And the reason we do that is because I've set it up in such a way that I can take what's persisted and use that to reconstruct the things that don't persist. Part of that idea of persisting as little as possible. So we have the pairs, keys, and values. They're stored together in pairs right next to each other so that we can sort of have better cache locality, better direct access to those. CHM stores sort of auxiliary data such as the number of free slots in that particular level, the total size in terms of how big that level is. And we have this mechanism where for resizing purposes, we have a pointer that points to a level and the level points to a newer level for expansion and reduction. So I'll go into a little bit more detail about how that resizing works later, but this is the general layout. So now let's talk about the resizing approach. So the resizing, and really most of this base non-persistent aspect of the design is based on CppCon's lock-free Java hash map. And so lock-free resizing is a challenging problem, especially in this case because keys and values are stored as separate atomic objects so that we can have larger keys and values. But what that means is that partial operations are possible. So we might perform a migration and not necessarily have the key and the value show up at the same time. So it's tricky to do that, but we managed to, the resizing scheme in CppCon's hash map accommodates that. When we do a resize, we will allocate a table that is typically going to be twice or half of the current table size and link that in as the new table. And key value pairs are going to be individually migrated. This process is concurrent, which means that multiple threads can work on this at the same time, and nothing's going to get in the way. If one thread is in the middle of, say, a migration, another thread can identify that and help that migration complete so it doesn't have to wait. It's parallel, meaning that multiple threads can do multiple relocations at the same time. And interestingly, it's incremental, which means that we can actually continue operating on these keys without actually having to perform a full table migration. Full table migrations are very popular in existing work, but if you do it incrementally, you can sort of amortize the cost of the migration. So the resizing, what it does is it will reserve a bit that's used in each value, and that bit will indicate that a migration is in progress for that key value pair. And if a thread sees that, then it needs to help migrate before it can actually return that value. It needs to finish that migration so that that key is migrated to that top level before it's done. But the problem is this resize bit cuts into our usable bits, so it's going to limit our values to 63 bits. But it's useful to be able to have this resizing scheme at the cost of that bit. Once the migration is done for that particular key value pair, the old slot's going to be replaced with a migration sentinel, and any thread that sees that will recognize that if they want to find the value associated with that key, that they need to go to a higher level. And also we have it set up so that once that slot is set as a migration sentinel, that means that you can't put another value in there. You need to go to a higher level. And so in that way, we can make it so that eventually we have migrated all the slots. Everything has a migration sentinel. We know that no thread can ever insert anything, and we can safely remove that particular level from our sort of scheme. So you can see in our example that we have one.dat, and that's actually been removed from our sort of linked list of levels because everything's been migrated. So I think sort of the more interesting aspect of this is how we added persistence. So we want to sort of more generally be able to add persistence to existing concurrent data structures. And it's kind of nice because we can leverage existing multi-threading guarantees that already exist. We already know that threads will view data in a consistent state relative to each other. We just need to extend it so that the memory also views everything in a consistent state. So here's sort of a naive initial idea that one might use, which is correct but not very performant, called flush on read. So flush on read has two rules. The first one is that if you create a new object, say like a node in a linked list, you need to persist the contents of that node and its pointer before you actually allow it to have access to shared memory. And the second rule is that before you perform a read, you always have to flush any persistent pointer. And the reason that's important is because if you're performing an operation that's dependent on that previous read, you need to make sure that that has actually persisted so that we can view it so that it has durable linearizability and crash consistency. So let's take a look at an example in some code. So persist will flush a memory address and fence it to make sure that we don't have reordering. When you perform a read, it will, like we said, we always flush before read. So we run the persist, and then we can load the address once it's persisted. In the case of compare and swap is performing both a read and a write. And so we have to persist before we perform that read, and then we can perform the write, and that write will not immediately be persisted. So in our example here, this is the same example we had from before where we had that issue with crash consistency. So we have node B inserted, and like I said, when you create a new object, you need to make sure that everything in that new object is persisted first. So we have node B persisted to node D right from the start when we first inserted it before we put it in shared memory. But when we change the pointer from node A to point to node B, we don't need to persist that right away. In step 2, we try to insert node C. And during traversal to figure out where node C goes, we'll persist on read that pointer from node A to node B so that we can figure out where node C goes. But we'll also persist the pointer from node B to node D, even though that's already persisted because our rule is to flush on every single read. And then we can insert node C with that next pointer already persisted, but the pointer from node B to node C is not persisted at that point. So maybe a better idea would be link and persist. So link and persist has that same rule as before where we flush newly created objects. But now what we want to do is we want to borrow an unused bit from a pointer. So most architectures leave unused bits, so we're able to do this. And by having it contained within that pointer, we can essentially have a flag that we can atomically update alongside the pointer. So now what we'll do is whenever we perform a write, we will mark that pointer as dirty. And when you perform the first read, a thread can see that that bit is marked and that it hasn't been persisted yet. So before it's able to succeed in a read, it first has to persist that location, and then it can return the cleared bit version of that value. And sort of the worst case this could have, so typically it's going to be on the first read, but in the worst case, all the threads try to read the same address at the same time. They all see that bit set and they all try to flush it. But in practice, it's normally just going to be the first read. So let's look at this example, same example again. So persist is very similar to before where we have flush and fence, but now we're additionally going to, once we persist, do a compare and swap to remove that dirty bit to indicate that that value has been persisted. And now when we perform a read, when we load the value, we're going to check for that dirty bit. And if it's not marked as dirty, then we know that something's already persisted it. And so we don't need to persist it again. We can just return the value. But if it isn't persisted, then of course we have to persist it that first time. And persist and compare and swap, same thing. So we have to load it because we're reading a value, check to see if that, that pointer has been marked dirty. And if it is, then persist. And then when we return a new address with our compare and swap, now we have to OR it, logical OR it with that dirty flag so that we can mark that we performed a write and we don't know that it's durable yet. So in our example, same as before, we have that node B that we inserted. And when we set node A to point to node B, we have to mark that link to indicate it's not persisted yet. So now in step 2, when we go to insert node C and we perform our traversal, we'll see that bit is marked. We will persist and then remove the mark from the pointer from node A to point B, to node B. And then when we go from node B to node C, we don't need to persist that again. We already know that there's no mark there. But then when we update the pointer from node B to node C, at that point, we will mark that as dirty. And then subsequent threads that go in can clean that. And of course, because we don't know it's persisted, so like in this case, at the end, we don't know for sure node C might be lost, but it's still okay because it's still in a consistent state that was correct at a previous point in time. So that example was dealing with linked lists. My hash map is array-based. And so the sort of concept for flushing new objects before introducing them is when you allocate a new level, you have to make sure that you flush all of the default empty values for that table at that level. And sort of a contribution of my work is to extend the link and persist to apply to data rather than just pointers. So remember, so this will also cost 1 bit per value. And if you remember, the resizing scheme also cost a bit. So this means that effectively we're limited to 62-bit values. We consider this a reasonable trade-off for our use cases. If you're doing, when we worked with Lawrence Livermore, they suggested that the scheme of reducing the persist was more important than necessarily having access to all of the bits. And if we really needed an object larger than 62 bits, that object could just be a pointer and that would be acceptable. So recovery. So when we recover, so our recovery works by only persisting the keys and the values. And we accomplish this because we can, the idea is that we can rebuild everything else. So the only other data that's made persistent, we use file system data to infer the content. So we use PMEM in a FSDAX mode, file system direct access, so that we can sort of memory map these levels as if they're files, but still have direct access to them through PMEM. And so as a result, we can infer certain data. So for instance, the size of the file we can use to figure out how big a level is. I've set up an atomic counter for the naming of each of these levels so that when you perform recovery, we know what order to actually reconnect the list of levels back together. And so we can use this to figure out that sort of information. And then for things like the number of keys that are currently in there, you can just, during recovery, iterate over that particular level to figure out how many keys are physically there, right? Because we already know the layout of this structure. So now let's talk about the related works that I compared against. So the most similar to our own is called concurrent level hashing. And this is also a lock-free design. It also uses open addressing, but it doesn't have open addressing on pointers. It only has them, or on values, it only has them on pointers. And it supports resizing like ours does, but it only supports expansion. You can't make it smaller down the line for memory reclamation. We also compare it against the hash map in OneFile. OneFile is a framework to convert data structures into weight-free transactional equivalents if they're node-based. So they have a node-based hash map that's in their design. that we compare against. We also compare it against just the STL hash map. It's volatile, and it's not concurrent, so we just use a global lock. This was just basically to have a baseline. And we also used the persistent memory development kit hash map. So PMDK has a lot of off-the-shelf persistent memory functionality, and so we leveraged that. It's based on the Intel thread building blocks concurrent hash map, and it uses reader-writer locks to accomplish its concurrency. Our testing environment, we used two 20-core, 40-thread Intel Xeon processors with 134 gigabytes of volatile DRAM and 248 gigabytes of persistent Optane DC memory. The Optane was configured in app direct mode with direct access mode so that we can map things to files. We also, of course, our code was written in C++ and compiled with GCC9. Our test configuration used 62-bit keys and values just to make sure we had parity with our limit of 62 bits. And our table capacities for open addressing options was 2 to the 14th initially, and we performed no garbage collection on our initial implementation just because I wanted to make sure I benchmarked the data structure rather than the garbage collection system. So now let's talk. So this is just an excerpt from my performance testing. So this is an alternating test. What it'll do is it'll fill the table up to about 50% capacity and then alternate between insertion and remove operations, 50-50 split. And it performs 400,000 operations, and we measure the time to complete. So the y-axis is the time to complete in milliseconds, lower is better. And so you can see our gray line PMAP tends to take the shortest to run, especially at scale. So that's everything I wanted to talk about today for the PMAP design. And I'll hand it back over to Christina. Thanks, everyone.
If I'm understanding, really the only thing you can map here is like an integer to an integer. Can I put a string as the value, for example? I mean, the way you're storing it has to certainly be.
Right. So the question was basically, does this only apply to integers, or could you apply it to something like strings? So in my base design, I'm doing just 64-bit or 62-bit integers for keys and values, but it's designed so that it can support arbitrary data types. So you could make it so that it was a pointer to, say, a string of arbitrary length if you wanted to. That would have performance implications, but it would work. I also didn't deal with persisting, say, whatever that pointer points to. So that would be a separate problem as well.
Right. So could you modify the design so that if you did have a string, for example, as a value, you could persist it directly, in the same memory with the key?
So the way I have it set up right now, the level is just on its own, and you would have to do a separate allocation if you wanted to persist that.
Okay. Last question. Flat map for performance reasons is a very common pattern these days, right? And in flat map, there's a separation between the key storage and value storage, typically. In other words, and it takes advantage of, cache, hotness and so forth by, doing things. Because a lot of times you're doing a query on the hash table that never involves the actual values as part of the observation. So in a large number of cases, you only ever have to look at the keys and you don't even have to look at the values you're reading. Have you tried anything with that kind of separation? Is it possible that it's faster?
So basically the comment was, have I tried using separating the keys from the values, since there are often cases where just the keys are accessed in a particular operation. So I haven't tried that, but I do think that that's very interesting, and I'd be interested in exploring that. All right, thanks everyone. I'll hand it over to Christina now.
Okay, I'm going to continue with persistent transactional data structures. So let's look at the taxonomy of transactional data structures. We're going to look at transactional versus non-transactional, and then also high-level data structure semantics, and then low-level reads and writes. So if you just want to write code with low-level reads and writes and you want persistency, all you really need is cache line write-back and sfence. You have to use those with caution, but they will persist your reads and writes. Now, if you want some data structure semantics, you need to include design using persistent data structures. And there's been several persistent data structures in literature that have been proposed. Now, if you want transactional support, there have been persistent transactional memories in literature, but they synchronize on the low-level reads and writes. One benefit is that if you synchronize on high-level semantic complex, you can get performance gains. And there was a gap in this research area. And so we filled that gap with persistent transactional data system for linked data structures, which we call Petra. So the design goals of Petra are that we want high performance, and we achieve this through low overheads added for durability, and then high scalability. We want performance that scales very well as we increase the number of processes. And also we want non-blocking guarantees. We want to guarantee that there's going to be system-wide progress. So to achieve high performance, Petra keeps the number of cache line fences and memory, the flushes and fences low by persisting only the transaction descriptor. So the transaction descriptor has all the information needed to execute the operations of that transaction. And so for this reason, if we just persist the transaction descriptor, we can leverage it as a redo log if there's a crash. And we can use that log to verify consistency and correct any possible inconsistencies. But this is optimized for the failure-free execution. So if there's a recovery, our recovery is quite expensive. And but we get better performance in the common case of no crash. And for high scalability, Petra achieves high scalability by doing transactional synchronization only for high-level semantic conflicts which are on the nodes themselves. All of those low-level conflicts, those can be handled using thread-level synchronization techniques such as like lock-free programming or locking techniques. This eliminates false aborts, so we get higher throughput because we get more committed transactions. Another optimization that we do is that we do a logical rollback. We don't need to revert back to the correct state after an abort, because what we do is we do an interpretation of the correct abstract state, and then we can make decisions based on that interpretation without the expensive physical rollback. Finally, Petra is non-blocking, and it's able to achieve a non-blocking technique in enforcing transactional synchronization by using a helping scheme in conjunction with compare and swap. So what it's going to do is when a transaction detects a conflict, it's going to help complete that transaction. It's going to go through every operation, and it's going to persist that transaction descriptor before going back to its own operation. And so this is how we are able to enforce transactional synchronization without explicit locking. And so this way we avoid potential deadlock scenarios or anything that might prevent progress. So Petra achieves obstruction freedom. This means that a single process executed in isolation is guaranteed to make progress. We're not lock-free because we have the potential for infinite helping recursions if two transactions attempt to access nodes in opposite order. So let's take a look at some of our type definitions to get a feel for how Petra is structured. So first we have a transaction status. It's either active, committed, or aborted. The persistent status is maybe, in progress, or persisted. So maybe means that we're still trying to do the transaction. We haven't even attempted to persist the transaction descriptor. In progress means that we've completed this transaction. We're trying to persist our transaction descriptor. So this way other threads can help us persist the transaction descriptor if they access a node that points to our transaction descriptor. Finally, persisted means that we've persisted this transaction descriptor, and all operations are considered to be persisted at that point. So our operation type is insert, delete, or find, because we're dealing with sets for this case. And then for our operation, we have a type and a key. So the descriptor, this is our transaction descriptor. It has a size, a transaction ID, a status, a persistent status, and then a list of operations. This is how other threads can help complete a pending transaction, because they can reference this list of operations and help complete it. And then we have a node info, which has a descriptor and an operation ID, and that node info is embedded in the node. So this is how all other transactions that access nodes can go and find that transaction operation list and help complete transactions. So here's the Petra methodology overview. First, we create a transaction descriptor, and then we start our transaction. So it's pretty straightforward. We just go ahead and execute our operations, and then we just keep going. If the operation is successful, we just keep executing operations. If any of them fails, we're going to abort the transaction to preserve that all or nothing property of transactions. Otherwise, once we've finished all our transactions, we're going to attempt to commit the transaction. And then we're going to set the transaction status using a compare and swap. And then finally, we're going to set the persistent status also using a compare and swap. And this is when our transactions persisted. So now I'm going to go into more details on this execute data structure operation. So before I get into the details of the execute data structure operation, I'm going to give a little bit more background on the underlying transaction management for Petra. So Petra uses lock-free transactional transformation, which we abbreviate LFTT. So LFTT is actually a lock-free version of transactional boosting. And what transactional boosting is it does high-level semantic conflict detection and uses, for transactional synchronization, using abstract locking. And then all thread-level conflicts, like traversing a list or trying to swing a next pointer, that's all handled using a base concurrent data structure. It could be a lock-free data structure. It could be a lock-free, locking or lock-free. But that's all handled using a base concurrent data structure. And so that's going to be indicated by the do underscore function. That's coming from the base concurrent data structure. So what we do here is we're going to start a compare and swap based loop. And then we're going to do a do locate pred, which means that we're using the base concurrent data structure to do a thread safe traversal to the node of interest. And so then we check to see if the node is present. So if the node is not present, that means there's no ongoing transaction. It's not even there. So that means we can just go ahead and do our operation from the base concurrent data structure. We didn't need any transactional synchronization for that. Now, if the node is present, then there could be an active transaction. And that's when we're going to call update info. Update info is the procedure that will go and check to see the status of the node's transaction. And if it's active, it needs to help complete that transaction, and it's going to take it all the way to persisting the transaction descriptor before even starting its own operation. So then once it gets to its own operation, the operation may succeed or fail, which is going to pass it back to that execute transaction function. But if our compare and swap fails, then we have to just retry that entire loop. So here's an example of Petra in action. So we have 3 threads. The first thread does an insert 3, insert 1. Thread 2 does an insert 4, insert 2. And then thread 3 does delete 3, delete 4. So each of these transactions have to create a transaction descriptor. And we assume that the list is initially empty. So for the first transaction descriptor, we have node 1 and node 3. And those descriptors are going to point to T1. So then thread 3 is going to come along, and it's going to do a delete 3. So now it has to point its transaction descriptor to T3. Thread 2 is going to come along, and it's going to do an insert 4. So that's going to point to T2. But what happens is when thread 3 does a delete 4, there's a conflict there. So it has to help complete thread 2's transaction. So if this were to play out, it would help complete the transaction, persist it, and then finish off its own operation. But that's not what happens in this example. In this example, we have a crash. And so what happens is that since T2 and T3 were never persisted, they're lost. Those are considered not persisted. Only T1 was persisted, and so that's the only one that should be recovered after the crash. So now I'm going to go into the recovery. So this is a pretty big flow chart, and as I said before, our recovery is expensive. So what we do is we have our persistent transaction descriptors, and so we're able to read them. So what we're going to do is create a KD map. This is a map that maps keys to descriptors. So what we have to do is go through each transaction and go through each operation, and we need to map it to the correct descriptor. So what's going to happen is as we start populating with descriptors, if the descriptor that we're looking at happens after the descriptor in the map, we're going to replace it because we want to know what was the most recent descriptor to access this node. And so we keep doing this until we've gone through all the operations. So now we're going to verify the consistency of whatever the remnants of that list was. So we're going to traverse through that list, and this is at the bottom part of the flowchart. And we're going to see if the node, the descriptor that is associated with that node, is the correct descriptor based on our KD map. And then if it's not, we have to just remove the node and execute the operation all over again. Otherwise, we need to check the value, the contents of the node. And if that's valid, it's consistent. Otherwise, we delete that node and just re-execute that operation. So we've tested Petra on Intel's second Xeon scalable processors, codenamed Cascade Lake. It has 48 cores, 2 sockets. It supports 96 threads. The main memory consists of Intel Optane DC persistent memory with 6 terabytes total capacity. And it also has 768 gigabytes of DRAM. And we place all persistent data structures in persistent memory. DRAM stores everything else. The operating system is Ubuntu 18.04. And then our application and microbenchmarks are compiled using GCC 7.4 with the O3 optimization flag and the C++ 14 standard flags. So for our microbenchmarks, we have the different operation ratios. Write dominated is going to be list and map is 40%. For list, we have insert 40%, map 30%. For list, delete 20%, and then delete's 40%, find is 20%. For the maps, delete is 30%, 10% update, and then 20% find. For read-dominated, we have our 10% update, 10% delete. For lists, we have 80% find, and for map, we have 5% update and 75% find. The number of transactions is linked list is 100,000. The other data structures is 1 million. And then for the key range, we have 10,000 for the linked list, and the other data structures is 1 million. We had to keep the linked list test size lower because it's an O of n time to do a traversal through the list, and that's quite a bit more than the logarithmic search time of the other data structures. So here's our example of our the results for our linked list and our map, and the left is the write-dominated workload, and the right is the read-dominated workload. We test for either transaction size of 1 or 4, and we're comparing Petra to a non-transactional durable sets, to LFTT, to OneFile, Romulus, and PMDK. So if we look at the linked list example, Petra performs the best and is the most scalable. LFTT also scales similarly to Petra because it's the underlying transaction management system for Petra. So the other transactional management, persistent transactional memories do not scale as well, and that's because they're synchronizing on the low-level reads and writes. The gap between the performance closes a bit for the read-dominated workload, and that's because the other persistent transactional memories are optimized for read-only, whereas Petra is still allocating descriptors for read operations, so there's no performance benefits for a read-dominated workload. And then for the map, since we're able to execute more operations, we're getting, the overhead of Petra starts to catch up with itself. And so the non-transactional durable sets and LFTT are performing the best here. And that's because non-transactional durable sets does not have the overhead of transactions, and LFTT does not have the overhead of persistency. And then once again, the map, we see that the performance gap closes a little bit, but Petra still outperforms the other persistent transactional memories. So here's our skip list and our MD list. It performs very similarly to the map. The Petra performs better than the other transactional memories, but the non-transactional durable sets and LFTT outperform Petra for the skip list. And then, but the performance trends looking at comparing Petra to the other persistent transactional memories is quite similar, with Petra still outperforming the other approaches. So here's our TATP transactional processing workload, and we compare Petra to OREC, ring STM, coarse grain locking, and then NoRec, and then the TL reader-writer lock. So Petra is the only one that scales well. The other persistent transactional memories scale to about 16 threads, and then they start to lose some scalability. And then the TL reader-writer lock, that scales quite well, all up until 48 threads is actually timed out, but it scales well because it doesn't require quiescence for the commit phase, so that helped it to keep its scalability pretty well up to 48 threads. So now we're going to do our live demonstration. And we're going to do this from our AMD EPYC server back in our lab in the University of Central Florida. It has 32 cores and 64 logical processors. For the compile options, I had to indicate that we need to use the DRAM allocator. And then for the persistent write-back, we have to change that to a cache line flush. And so if you look at the code below, what we do is we define that PWB as a cache line flush. So we have to do an inline assembly call for the cache line flush. And then that provides strong enough ordering guarantees that we don't need to really assign any instruction for pfence, and then we don't need the psync. So this is not a persistent memory system. So our micro benchmarks include an operation ratio of 33% insert, 33% delete, and 34% find. The number of transactions is 10,000, and our key range is 10,000, so that the test doesn't take too terribly long. So let me go to the test. And make sure I'm still connected. We're gonna have to re-access the system, and then we're gonna go to the correct directory. Okay, so we're gonna run the script. And then run our GNU plots. Okay, so we're starting off with the list, and we're only going to go up to about 32 threads. We can see that Petra is scaling quite a bit better than the other approaches. We're comparing to Romulus and one file, and that's because Romulus and one file synchronize on the low-level reads and writes, and so Petra is gaining a lot of scalability because we're only doing transactional synchronization for conflicts on the nodes themselves. And also we're benefiting from a logical rollback. And so we can see that Petra does quite a bit better than the linked list. The others are going to go quite fast because their logarithmic search time is going to make the test go fast. So I'll just have to talk about those one by one as they finish. Okay, I think it's all done. So we've already talked about the linked list. The skip list is, so we get a lot more throughput because we have a logarithmic search time, so we're seeing much higher numbers here for operations per second. We're still seeing the same scalability for Petra, and so that's due to the high-level semantic conflict detection. Then for, let's go to the MD list. Okay, the MD list did not, okay, sometimes it will clip it a little bit. So what I'll do is, let me talk about the map, and then I'm gonna just run the plot script again. It should show everything. So for the map, the throughput starts off really high. That's because at this single-threaded case, each transactional persistent, the chance of accessing a different node is quite high. And so if there's no conflicts, all the approaches are going to do very well. And so we actually see Romulus and one file doing much better because they don't have conflicts. But as we introduce more threads, we're getting more conflicts on keys, and so that's when we start to see Petra outperform the other approaches. So even though it looks like we tank in performance, we still have a very high operation throughput. It's just that we're dealing with conflicts, which always slows everything down. Let me just run the plot script one more time to see if I can get the full MD list. It just eclipses it sometimes. Yes, the MD list is full now. So let me just look at the MD list. All right. So for the MD list, it's very similar scaling. How the MD list is structured is that it has it arranges all the child nodes in n-dimensional space. So this is like a logarithmic search time. So it's going to perform very similarly to the skip list. And once again, we see that Petra is outperforming the other approaches due to its high-level semantic conflict detection. So I'm going to pop back into my presentation, and we're going to finish it up. So the key takeaways here are that persistent memory provides a new tier of memory. It's non-volatile, it has high capacity, and the access latency is very close to DRAM. So this makes it a very practical memory for many use cases for scientific applications that are dealing with large quantities of data that have computationally expensive operations. And our persistent hash map, it uses open addressing. So this provides a low memory overhead and improved cache locality, which is also very essential for graph processing workloads. And then Petra provides very high scalability, scalable, durable transactions due to its high-level semantic conflict detection. And so the source code for our persistent map is available at the UCF GitHub PMAP. And then for Petra, it's available under my GitHub handle under Petra non-PMEM. So this concludes my presentation. Are there any questions? Yes?
You mentioned that Petra uses a transaction descriptor for read-only transactions as well.
That's correct.
Is that something where you could introduce the concept of an invisible read, or does semantics and Petra require that you actually have that transaction log?
Yes. So the question is, since Petra requires a transaction descriptor for reads, and that introduces overhead, is it possible to treat some reads as invisible or do some sort of optimization to eliminate that overhead of the descriptor? And we did look at this option for the read-only transaction case. What we could do is we could decide that we were going to pick like a serialization point like at the beginning, so that we would always assume that we would look at the current state and always like kind of backtrack to the older values, so that anything that happened during that transaction, we could just assume that transaction like linearized at the start of the transaction. And so we can like do a read where we read the old value, just assuming that we're linearizing at that beginning of that transaction. And so that would help us for if every single operation was read only. We can't do that for if they have any write operations, because then that could potentially conflict with another transaction. And so we can't just make that assumption that it linearizes at the start. So that's the case that we were able to look at some optimizations for. I think Kenneth did this for his transactional vector that he had done. So we did actually implement this, but we couldn't think of any other ways to avoid the descriptors for reads if we were going to have some writes a part of that transaction. But we are definitely, if you have any ideas, we are very welcoming. Yes?
A clarification. The difficulty is that you get this transaction, you don't know ahead of time whether it's read-only until you get through it. Is that what you're telling me?
No, we know ahead of time that it's read-only. And so what we do is we just assume that the transaction's going to, with a linearization point, it's kind of like the point in which the transaction takes effect. So we just make an assumption that the linearization point is right at the start. So we always, when we access a node, we always read the old value because we assume that we linearize at the very start. And so that way we don't need to do the whole like synchronization with transaction descriptors for the read-only case.
Read-only, this transaction read-only or the whole workload?
The individual transaction is, so the question is it the whole workload or just the transaction? And the answer is that it's just the transaction by itself is a read-only transaction. Yes, you're welcome. Yes?
So I think this, I don't know if you've studied this kind of workload, but in some non-trivial systems these days, there are workloads that are sort of write once, read many. Do you have an opinion on whether persistent memory would be a good choice for that?
Okay, so the question is, there are some workloads with, is it write once, read many?
Yeah, so basically think about IoT telemetry, for example, right?
Yeah.
Getting a measurement on the sensor in a time order thing, and you just write that, you never update it, but then you might have analytics that are going to look at that, and over the long period of time, you probably want to flush that to another tier of storage, right? Because it becomes less valuable later.
Yeah, it seems like you would definitely want kind of like a hybrid design where for that like write once, read many, where you might want to maybe start it in persistent memory and then migrate it to the like NAND SSD when you're not touching that memory. So I would think a hybrid design would be the way to go for that. I haven't looked into that, but that is something I would look at for future workloads for micro benchmarking. So thank you for that. Any other questions?
There is a question from online audience. Does the performance analysis include any resize operation?
Does the performance testing include any resizing operations?
Right.
So for the data structures that I tested, there was no need to resize because they were list-based. But Kenneth, his vector, Kenneth, did you have any resizing? Don't turn it on. You come up here before you turn it on.
Yeah, so I guess that would be a question about Petra or about PMAP. Because if it's about PMAP, there is resizing in PMAP. I didn't test it extensively. I don't have results on that. I was more concerned about it being correct and not having to just totally stop what was going on. But I don't have any specific results. All right, no more questions? All right, Mr. Sam. Thanks, everyone.